Okay. Good morning, everyone. Welcome to our today's Nano seminar. We have a special guest from Holon Technology, Israel. It's my pleasure to introduce Professor Laikhtman. Laikhtman is an associate professor in physics in Holon Technology in Israel. He completed all his academic studies in Technion, Haifa, in physics chemistry department. After completing postdoc research in CNRS, France, then in the Space Environment Division of Forex in Israel. In 2007, he joined the Physics Department of Faculty of Science in Holon Institute of Technology as a senior academic staff member. In Holon Institute of Technology, Laikhtman is in charge of the Materials Analysis Research Laboratory equipped with scanning tunneling microscopy, atomic force microscopy, scanning electron microscopy, and micro-Raman instruments. His academic tasks include teaching of undergraduate physics courses, the graduate nanomaterials course, academic responsibility for students' physics labs and physics demonstrations. From 2015, he holds the position of Vice Dean of the Faculty of Sciences. His research interests are in the field of nanoparticles, characterization, processing, as well as advanced materials, micro and nano analysis. Laikhtman published more than 50 papers in peer-reviewed journals and established a number of collaborations within the European research networks. He is continuously invited to give plenary keynote and invited lecture at high-level scientific conferences. Welcome again, Alex, and the floor is yours.
Thank you very much for this introduction. Thank you for coming to attend this talk, and thank you for inviting me to this excellent place in the Sunum and Sabancı University. So I will now go to my presentation. So I will talk about hydrogen interaction with inorganic nanoparticles, and I will talk it in the sense of energy storage and also functionalization of these nanoparticles. So this work is divided to several parts, and first I will start about some brief description of the materials that I'm working with. So we're talking about what's called inorganic fullerene-like nanoparticles that you can see on your left side, and inorganic nanotubes. Both of them are made from WS2 tungsten disulfide, and they have both common and different properties, this and that. So in the case of fullerene-like nanoparticles, these are multi-layer structures. They are called sometimes giant nanoparticles because they have their sizes from 100 to 350 nanometers, and there is some hollow core and a lot of layers which we try to use for implantation of different species. In the case of nanotubes, these are multi-wall, quite long nanotubes of up to 20 or even more microns long, and their widths range from 50 to 120 nanometers. They have also open ends, so there is some possibility to introduce the species from their ends and also through the defects. Just a few words about the synthesis. So the synthesis was developed starting from 1992 in the laboratory in Weizmann Institution in Israel of Reshef Tene. And there was a Nature publication about this, and the scale up was later developed in the Weizmann Institution, also in the startup company by my now collaborator Al Azak, who is now also a dean of the faculty in the charge of the synthesis laboratory. So this is a multi-step process that we start from the oxide, and through oxidation reduction reaction, both fast and slow, we finally come from the outside to inside to conversion of this oxide to WS2. We start always from outside to inside until we get this fully covered WS2 inorganic. We call this fullerene-like nanoparticle. just to guide you in, it's very different from WS2 or MOS2 materials that are known for tens of years and sometimes used even in commercial products like lubricants in oil. So this is the same stoichiometry, but very different structure. In the case of nanotubes, the chemical part is about very similar. So again, we start with oxide, but technologically it's very different, though it's made in the same reactor. So again, we start with oxide, and we first produce the nanowires or nanorods of the oxide, and then starting from this nanorod, there are layer by layer of WS2 that are formed, and we have these multiple nanotubes with open ends. So, and this material should be pure for at least more than 90% of purification, both in their structure and in chemical composition. Sometimes we have some oxide, but generally we can remove it up to very low concentration. So I will discuss a number of applications. First one is for our attempt to use them for hydrogen storage. And the next one, based on this hydrogen storage result, for doping for electronic and mechanical applications. So this part of research for hydrogen storage was made with a number of collaborators, both from HIT, the Plasma Lab, from Republic of Korea, who provided us with measurements of hydrogen inside. Also, we did a lot of collaboration here with this institution, Sunum, with Meltem Sizem, who assisted us with a number of measurements. And also a great contribution is from the theoretical group in Spain, Julio Alonso and Jose Ignacio Martinez, who assisted us with theoretical simulations and modeling. Because we are experimentalists and they are theoreticians and they are specialists. So why we decided to try to use these materials for hydrogen storage? There are a number of criteria that fit this task. For example, they have late structure in hollow cores, or a lot of space to contain these materials. So hydrogen could be, in principle, intercalated in between the layers or diffused into the hollow core. Or there are a lot of surface defects which also can guide the molecules, hydrogen molecules or atoms inside. And there are interstitial porous spaces between the tubes. So these nanotubes, they are characterized by high thermal stability, both in air and vacuum. So we can both process them for hydrogen storage and then for hydrogen release without compromising their structure. Also high chemical stability, high mechanical resistance to use in various devices and instruments and batteries and so on. Simple dispersion, good adhesion to polymers, also to attach to other materials. And what's the most important is they can be now synthesized in commercial quantities from about 2009. Just before 2009, they were synthesized in micrograms and milligrams and also not more. So they were not very useful for industry until in 2009 the scale-up process was developed, and now there are even commercial companies where you can buy these materials. They produce tens or hundreds of kilograms per day. Though if you buy from them, they generally sign you on some paper that you cannot do any research. In our case, in our labs, we produce them not for hundreds of kilograms, but for hundreds of grams or for kilograms of better quality. And generally through our collaboration, we don't need people to research. A lot of science was made from that. So as I have just told, we're not the first who tried to use them for hydrogen storage. There was a Chinese group in 2003 who already published some results of hydrogen storage in this or similar type of nanotubes, either MOS2 or titanium S2, and they achieved some results by different methods, though these results were not verified by precise techniques, but they very fast discontinued their research for the same reason that I have just mentioned, that in 2003, these materials were not available in more than milligrams, so there were no any interest from industry for their applications. And we decided to resume the experiments about 9 years later when this problem was resolved. So we started with very simple hydrogen exposure, just at high pressure, either high temperature, room temperature, or low temperature. So our first results were not very promising. So though we proved that some hydrogen can be absorbed in these materials, but the weight percent was very low. There was about 1.15 weight percent at room temperature, even not so good at high temperature. Though we have to note that the molecular weight of WS2 is very high, 148 grams per mole, while hydrogen is just 2 grams per mole. So very low weight percent means still quite high atomic percent. When we lowered the temperatures to either liquid nitrogen temperature or dry ice temperatures, then we achieved much better results, and not for the lowest temperature, but some intermediate one. I will stop on this point. I will concentrate on this point later, because we have some competition between adsorption and diffusion. But again, this type of experiments did not provide us the best result that we are expecting. So here I will jump to other methods. So we applied hydrogen enhancement by plasma, radio frequency plasma and microwave plasma, and then we jump to more than 1 weight percent. And I will talk about this result, which is quite a nice result for this type of material. So plasma really enhanced the results of this hydrogenation. Now I will talk about theoretical simulation. So how they provide this structure. So our colleagues from Valladolid, they calculated both Fullerene-like nanoparticles, so the multi-layer structure, and the nanotubes. And so we achieved the perfect stoichiometry, which is related to our experiments. So the interlayer distance, the number of atoms, and so on. And then they calculated the absorption of hydrogen, the energy of hydrogen absorption. And then for physisorption just, we obtain the positive absorption energy, and the positive means that it's favorable. The process is exothermic, so this we can easily achieve this hydrogen physisorption on the very surface of both nanotubes and Fullerene-like particles in this way, and either in very different configuration. The problem that if we have only physisorption, we would have only 0.02 weight percent. Experimentally, we obtained much better. So it's good that we started our experiments from our study from experiment and from theory, because theory was quite discouraging. And for experiments, we had 1.2 weight percent, so we have to consider some more configuration other than just physisorption. The first one, if hydrogen is absorbed in more than one monolayer, which is quite beneficial for hydrogen release, because we don't want just to absorb hydrogen. If we would like to use it, then we have to easily release it. And indeed, the calculation showed that hydrogen can be absorbed in 2 or even more than 3 or 4 layers. It's quite stable at room temperatures. And the energy of its absorption is still quite low, but positive. So this is indeed the case when hydrogen molecules are on top in a number of layers. But it's still not enough. Another process that we considered to be the major one is intercalation of molecular hydrogen, so the hydrogen molecule with not dissociated hydrogen molecule in between the layers of WS2. However, we were quite disappointed by these calculations because they show that the energy is very, very negative. And this is because we have to increase the interlayer distance from 6.2 angstroms to 7.5 angstroms. And the energy required for this is very, very high. This is theory, but sometimes the experiment, what is forbidden in theory is allowed in the experiment, as we have plasma process with quite a lot of energy. And when we measured our nanoparticles by, for example, TEM, then we indeed observed exactly this extended interlayer distance of about 8 angstroms as compared to 6.2, 6.5. So though theoretically quite unfavorable, but this process takes part in reality. So we do have some interpolation of hydrogen, and there is a lot of space for hydrogen inside. So this can be one of the mechanisms. And another one is diffusion of molecular hydrogen, also from one location to another. This is more related to our measurements at low temperatures, because diffusion is quite favored by high temperatures, but absorption is by low temperatures. So we always have this type of competition. And so we calculated the diffusion barriers, and these diffusion barriers are very low. So they are the range of KT of Boltzmann distribution, and indeed at very low temperature, the absorption is okay, it's quite favorable, but diffusion is very slow. At high temperature, the absorption is not so favorable, but the diffusion is high, and in some kind of intermediate temperature, we have some optimal point. Here are the graphs and the diffusion path is as calculated. But we always consider that atomic hydrogen may absorb better than molecular one. And the calculations show that indeed absorption of atomic hydrogen is much more beneficial. We have very positive energies. There is, however, one problem. We don't have any bottle of atomic hydrogen. We have molecular hydrogen, you cannot find a bottle of atomic hydrogen because it's not stable. And then you have to pay a lot of energy to dissociate this hydrogen. It's 4.5 eV on the surface. It's slightly lower, 3.8 for eV, and still in total, in netto, you pay more than you get. So if you already have some atomic hydrogen, it's very useful. But if not, the energy is the process is not so beneficial. Though plasma process may contribute it largely. So we calculated both interpolation of atomic hydrogen in nanotubes and in nanoparticles, and still there is a problem that already we should have some atomic hydrogen from other process to be inside, and also our measurement did not show any chemical bonds between hydrogen and WS2. Which means that there is not much atomic hydrogen associated. Though in the case of nanotubes, there is some process which allows its production and then dissociation when it is already inside, and then there could be some process of relaxation, again to molecular hydrogen. And in this case, the process is energetically favorable. So there is some kind of multi-step process. First, dissociation of hydrogen, and then it's relaxation inside the materials, and then we have, again, a lot of space for hydrogen interpolation. So this process could indeed take place according to these calculations. Then it's not surprising that we don't have chemical bonds between hydrogen and sulfur, as because of this relaxation again to molecular hydrogen. So anyway, the atomic hydrogen is much more advantageous. So how can we get it? First is atomizer, but it works well only in UHV systems. And then plasma hydrogenation, either microwave plasma, but it proved to be sometimes very aggressive, or RF plasma, radio frequency cold plasma. And then for this cold plasma, we have two instruments in our labs in physics department, HIT, through our collaboration. We use mainly this one, this one of helicon plasma source at low pressures, and the temperature did not get more than 35, 40 degrees. So these are some type of high school calculations for the plasma conditions that we need to apply. And finally, it was a task to prove that this type of hydrogenation indeed produce some hydrogen inside. So we first measured by some normalized way the desorption of hydrogen in situ. So inside the plasma reactor, when we expose them to hydrogen, then we heated the samples and we proved that only hydrogen can be released. We also did these experiments with deuterium to be sure that this deuterium hydrogen comes from our processes and not from somewhere else. Also, it was confirmed by TGA. By the way, TGA confirmed that our nanoparticles become hydrophobic, which is very good for applications. Otherwise, they absorb in air a lot of water, which is not very beneficial. And again, it was also chemically proved by micro-Raman when we measured hydrogen molecular bands, Raman bands, which is very difficult to measure, or deuterium bands in our structures. And we also proved that when we anneal these samples to 450 degrees, these bands decrease, so they indeed are related to molecular hydrogen in our sample. This measurements was very difficult because the cross sections for molecular hydrogen are very low in Raman, and so we need to apply very long measurements. But anyway, we succeeded to do this and to prove for our findings. So how the experimental concentration of molecular hydrogen reached higher values than predicted. So first, we have more than one monolayer of hydrogen, and then, as I told, though intercalation is not an energetically favored process, but because of plasma and because of defects and pores in our materials, there is some penetration of hydrogen. But there is one more property that we discovered for our hydrogenated materials. When we have just one monolayer of hydrogen on the very surface, this one monolayer induced the expansion of between the layers in the deeper layers, and then we will use it for another part of our research that I will talk in a few minutes. So already the hydrogen absorption, we gained a lot of energy that otherwise we have to spend on the expansion of this layer. So this process is very beneficial not only for hydrogenation, but only to introduce different species inside the nanoparticles structure without a lot of energy being involved. And also we proved our micro-Raman by measurements of this chemical structure by theoretical calculations, and we showed that the peak position is also related to concentration of hydrogen molecules inside the samples. And here are the conclusions of this part of the talk concerning the hydrogenation. So there are a lot of hydrogenation methods that we can apply, but the best one is to use either microwave or even better and more gentle is radio frequency plasma. In this case, we achieved more than 108%, which is quite good for this type of materials. Of hydrogen, also there is always competition interplay between absorption and diffusion of hydrogen, and the intercalating of hydrogen molecules between adjacent layers is quite an endothermic process, but it can take place because of plasma and defects, also because the previous hydrogen absorption. And if you already have some atomic hydrogen, it always would be beneficial. So, and then based on this increase of the interlayer distance by initial hydrogenation, we use this property to a different type of study, which was also initiated here in Sunum. And this was related, this study was related that these WS2 and MOS2 nanotubes can be used as commercial lubricants and also in various electronic devices. And this could be done by controlled doping of rhenium, niobium, or gallium. So they can improve the electrical response and the electronic properties. And so one of our research tasks was gallium implantation in WS2. And this was done here in Sunum about 8 years ago in collaboration with Laikhtman, and also Ferai also took part in the later stage of these experiments. And again, very recently, with the help of our theoreticians collaborator from Spain, we achieved some results that fully confirmed then the results of that experiment that otherwise were not so clear. So first of all, the doping methods. So we did not arrive to gallium implantation by focused ion beams immediately. So we tried different chemical methods. And these chemical methods, for example, with rhenium, were quite successful to decrease the specific resistivity of our nanotubes. And this was very beneficial for their lubrication properties because of column repulsion. But the process was quite difficult, chemically difficult. And then different ion sources were used for both rhenium and other atoms implantation. But the distribution of these atoms was not very homogeneous and the results were not continuous. And then we decided during my stay here to try to use focused ion beam to doping of gallium. This is a device here. It's still, I don't know if it's still the same device, it's still the same machine. Yeah, but we applied this. Yeah, here are a few words. So people from this subject, they know much more than me. But here are the mechanism of gallium implantation through a number of processes. So generally, energies of 5 to 30 kilowatts of ion beams are used. And because gallium is quite a heavy atom, it can both release some other materials, but also be implanted inside. This process of gallium implantation is of our interest. So the first results were not so good because we tried to use very high ion doses, and then there was a lot of amorphization and melting and destruction of material structure. And then we tried to use lower doses. But for lower doses, we did not get any gallium inside as measured by electron dispersion spectroscopy in SEM. And then for some reason, we tried to do the same procedure for previously hydrogenated fullerene like WS2. And surprisingly, surprisingly for us, we got this atomic percentage of gallium. The weight percent is about the same. It seems not very high, but for implantation, these are quite good results. What was most important, it was very homogeneous. So there were no gallium-free areas as detected by EDS. And the structure was nearly perfect. So there were no changes in the structure just for higher ion doses. Here you can see some improved experiments with weight percent of gallium. And the interpretation for this successful implantation was expanded interlayer spacing because of that previous hydrogenation of materials. So here you can see some simulations. So gallium implantation requires increase in the interlayer space from 6.2 to 665 angstroms. Quite a lot of energy, but we already did this by hydrogenation, most of it. So in this case, we can achieve up to 0.7 atomic percent of gallium. So even more than we got through the experiment. So there is some place to improve the experimental procedure. And these are due to formation of gallium S bonding, and here you can see some results about the amount of gallium in relation to its percent of monolayer. So we need to pay for expansion energy, but we gain in implantation. And these are our results. So this was quite confirmed by Micro Raman. We did observe these modes of Micro Raman, which confirm this theory. And so I would like to conclude that because of that previous hydrogenation, we now open the gate for functionalization of these nanoparticles, also for electronic applications. So we can implant gallium and other species at quite not so extreme conditions, and then to achieve much better electronic properties. We already did some electrical conductivity measurements, which proved that these nanoparticles have better conductivity, better electrical conductivity, less resistivity, less surface resistivity, and then so can be applied in a lot of devices which otherwise require much better electronic property that pure nanoparticles. Okay, there is another part of the talk, but I think I will finish now. So, yeah.
Just like 10 minutes.
Okay. So if we are talking about the functionalization of nanoparticles, we did some quite a different study. This was used for mechanical properties. The Teflon coatings of WS2 nanotubes. Nanoparticles, not fuller and like nanoparticles of WS2, they are already used for lubrications because they are just ball-like nanoparticles, so they can indeed decrease the lubrication. But what about the nanotubes? Generally, nanotubes are not so beneficial for friction reduction because they are easily broken. But then some of us proposed to coat them with Teflon. So there was some experimental procedure for chemical procedure of coating the nanoparticles with Teflon, and of course we controlled them both in by microscopy and chemically until we obtained a structure with not a lot of agglomeration. So all nanotubes were quite individually coated with this Teflon material. These are full experiment which I not go through. So the first part was successful. And now we had to characterize them. So first we considered their resistivity, which decreased quite a lot. Again, as in the previous case. Sorry. So not resistivity, the friction coefficient, and also their stability at high temperatures, because in friction you generally achieve very high temperatures. So the temperature stability was quite high until about 500 degrees. Only then there was some decomposition. And also the content of the nanoparticles proved to be they were very pure, and just there was some Teflon outside at sometimes at mostly measurable quantities. And as I just told, no weight loss was in nitrogen gas atmosphere, so stability was proved. And then we measured the friction coefficient under different standard experiments, standard method. And this friction coefficient of these nanoparticles went down with the increase of Teflon concentration. PaO is some kind of polyolefin oil which is used for friction experiments. And then the content of nanotubes added to this oil and then coated with Teflon decreased several times friction coefficient to nearly 0 levels. Okay, So 0.15 is quite good for this type of materials. And what's again, after friction coefficient, the amount of carbon inside the tracks was quite lower for these Teflon coated nanoparticles, and means the stability under friction was quite good. We also proved measured the elemental composition both in the nanoparticles after friction, before friction, and inside the wear tracks. And this composition again proved to be that if we have the best coating, that the properties are also the best. So they are stable, they reduce friction, they are stable under heating, so even at very high temperatures, 400, 500 degrees, we still have their high stability. So the chemical structure again was proved by micro Raman. So we detected these two peaks. They are very characteristic to WS2 nanotube. So according to their position and also to their relative height, we know that the crystal structure of the nanotubes was not compromised. But also we have some Teflon, very few Teflon, very on the limit of micro Raman detection, because micro Raman detection is about 1 micron, and our Teflon layers were much thinner than 1 micron. So, but we proved that there are no oxidation, no destruction of the structure, and this presence of Teflon structures in the contact interface, namely resulted in shearing and reduces and responsible for reduction of the friction coefficient. So now I just conclude this part and my talk. So we successfully functionalized the WS2 nanotubes with the Teflon coating in sonic bath solidification. TEM analysis indicated much better distribution of this nanoparticle as compared to pristine nanotubes. They were clearly absorbed, Teflon nanostructures were clearly absorbed, the friction coefficient decreased, and deterioration of Teflon coated nanotubes is quite low, but if it takes place, it even facilitates the penetration to the contact interface and contributes even more to the friction. So still there is a lot of work to do to improve this process and this property, the process, and to study of it, but already published this work, and already some industrial partners, they are quite interested in the process to be involved in their products. So most of the funding to this project came from European cost actions. We have also some initial grant with the Republic of Korea to initiate our studies of hydrogenation, and a lot of work is performed through our personal collaborations with groups throughout the world. And yeah, sorry. The last. Yeah. Now just want to say that
Sorry, Professor.
yeah. Yeah, I just want to take this opportunity that our institution, our department, and also electronic engineering department, every year we organize the conference, international conference, nanotechnology from academia to industry. I think Ferran and Meltem, they once invited them for to have talks. It's the conference only invited speaker, all speakers are invited, but we always invite students, postdocs, and young researchers to present their posters, and we even have support for poster prizes for them. And the next one will take place in about 3 weeks from now. By the way, the poster submission is still available this month. The registration is free, and I hope the next year will be also free. And this year we'll also have support of the Israeli Ministry of Science and Innovations. And these poster prizes are supported now by the Journal of Advanced Composite Materials of Springer that decided that they would like to give their support to best posters, even not in the field of only the field in the composite. So all of you are invited to attend this one. There is still some time, or the next one that hopefully will take about the same time next year. So thank you for your attention.
Thank you very much for this very informative talk. We have still time for questions. Are there any questions?
Yeah. I want to ask you, is it
Sorry hocam.
Your products, hydrogen storage,
Yeah.
the product you have made, will it be possible to use them commercially on MFC, proton exchange membrane fuel cell systems?
Yeah, I cannot answer this question about this specific time of projects, because this was not done to commercialize them immediately. As you see, the weight percent of hydrogen is about 1.5 weight percent. It's what the maximum. Generally, in industry, you need to at least 3 to 4 weight percent. Or again, I tell that molecular weight is quite high. And if we go to, instead of WS2 to MOS2, which we can also produce, though still in less quantities, but the structure is about the same, that it may be beneficial. Concerning your specific question, the proton
exchange fuel cell systems.
Proton exchange fuel cell. Okay, this one I cannot answer you specifically, but now we have some research of using this. These nanotubes as electrode coatings in hydrogen evolution reaction, and we already got some very promising results. But concerning using them specifically in fuel cells, unfortunately, I don't have a specific answer. We did not consider this type of commercialization in the short stage.
Okay, thank you.
Have you studied a temperature change on the tungsten activity?
Sorry hocam. Could you repeat it with microphone?
Have you studied the temperature change on tungsten nanoparticles? Because by increasing the temperature, tungsten behavior changes.
Oh yeah. This is quite well known, because the pure tungsten maybe, but the WS2, they are absolutely stable. In air, you can safely heat them to 300 degrees. You may have some oxidation, which is easily removed. And in vacuum, you can heat them to about 1,000 degrees without any change. There could be the main problem is atmospheric water absorption. So this is why before any experiment, we had to heat the samples in vacuum for about half a day at 120 degrees to be sure that all absorbed water is removed. But by the way, after hydrogenation, for some reason, they became hydrophobic. So we even transferred them throughout the world in not very hermetical packages, and this was fine. Yeah. So these disulfide structures are, this is not a problem for them.
Thanks for sharing the results. Actually, I was going to ask the same question. Like, how does it compare with the commercial or the very high performance hydrogen storage materials, which you answered?
If, again, if you compare them with materials based on platinum or palladium, of course, it's difficult to compare because they can be used at much, they have much higher hydrogen content. The main benefit of this type of materials is their chemical stability, their physical stability, and the ease of release of hydrogen. Because as we also measured one of the graphs that I showed, it's quite stable up to about 40 or 50 degrees, and then it can be easily released at high temperatures. And also what's important, maybe I did not stress this, that all these experiments were performed several times. So the process can be, after hydrogen release, we can use them again, the same materials, the same nanotube, the same nanoparticles. We can use them this again and again and again for the same process. At least we checked some of them for 10 to 15 times, and we did not have any decrease in their, or any modifications in their structure. So the hydrogen content is still not the highest, and so we did not consider them now at the commercial project for hydrogen storage, but we use this data for of hydrogenation for that it facilitate the introduction of other species for different applications.
And also, are there any functional groups on tungsten disulfide?
No, these are pure inorganic materials. So there are
no. The band gap?
The band gap is about 2 V. So these are, yeah, these are, they are semiconductors, but some intermediate band gaps semiconductors. It's between 1.8 and 2 V.
So you can attach molecules
chemically on the surface. Yeah. Now I understand your question. So yeah. They don't have any functional groups when they are produced, but you can have, you can functionalize them, for example, as we did with the Teflon. Though in the case of
wrapping, that's physical wrapping.
Yeah, this is physical wrapping, so we did not get any chemical bonds. Yeah, yeah, it's true. But there are a lot of works of putting some functional groups on them. Not this one, but it's fully done.
Understood. Thank you.
Thank you very much for this nice talk. So, I have two questions when you were showing your slides. One is, you talk about this expansion of the structure. So is that because when you take in hydrogen, that this is actually doing some mechanical work, or it's a consequence? How do you measure this? So experimentally.
Okay. Experimentally, in fact, I cannot clearly answer this question. So you initially ask what's other this expansion is the reason for. If the hydrogen is the reason for this expansion, or there is some mechanical expansion because of some hydrogen pressure on the material. I cannot fully answer this question. So experimentally, it was measured by electron diffraction and sometimes by TEM. Though in TEM, it's on the limit. In the electron diffraction, we obtained this, we clearly obtained this increase from 6.2 to 6.4, 6.5.
Does it correlate with the radius of the hydrogen ions or atoms?
Yeah, sure. It was fully, these structures, may I go back?
Why I'm asking this, because this hydrogen intake, is it like one of your barriers? Because the expansion of your structure costs you probably some elastic energy, and does it become one of the barriers for the hydrogen capacity of your material?
Yeah, this one is concerning this hydrogen absorption. So here in the modeling, so this is density functional theory modeling. So they modeled the stationary state. So we cannot model the process. We cannot model only the final state and its ground state. It's not excited.
You look at the thermodynamics, so before and after.
Exactly. So we cannot answer you. I cannot answer the reason why it happens, but just the consequence of this hydrogenation. So here, when we see this, this is interpolation, and I need this one here. And here you can see that the interlayer distance it increases because of this hydrogen coverage. So these are the distances between the atoms. These are not interlayer distances. These are distances between the W and the S atoms and then hydrogen. And here the calculated interlayer distance, which goes from 6.13 to 6.21 angstrom for full coverage of hydrogen layer. So this calculations, indeed, as you told, it's a consequence of this hydrogenation. We don't know. I guess it's because of some space that the hydrogen on the surface and its pressure on the neighboring layers. But
I do. It might also be interesting because so you talked about barriers, and so I'm also just speculating that maybe some colorimetric measurements, on these samples, like precise colorimetric measurements, might also provide you with some information about your barriers, like starting from cryogenic temperatures all the way up to whatever temperatures you're interested in. I just had this impression that this mechanical expansion of your systems might actually itself start to become a barrier for your intake or concentration, maximum concentration that you can achieve. Just a thought.
You're right.
My second question is about the last part of your talk. Was that like some lubrication development, or is it a surface coating?
Okay, it was the coating of individual nanotubes. So it's the surface in the sense of the nanoparticle. Because this nanoparticle, they are conglomerate. This you see this as just a powder, but it resulted indeed in the lubrication.
So it is actually intended maybe as a lubricant.
Yeah, it's exactly because
surface modified.
So first it was coated by Teflon, and then the decomposition of some nanoparticles inside the wear tracks, it provided even more reduction in the friction. So the high stability, it's not the excellent one. So we have to also to interplay between the stability of these nanoparticles, but also to allow some of their decomposition, and so they are the residuals are in the wear tracks, and they provide some kind of lubrication by decreasing this wear and resistant friction problem.
Thank you very much.
Thank you, Professor Alex. One of our Zoom participants, Idil Kula, has a question. I work on data sustainability and sustainable AI issues. Can we store data in fluorescence like nanoparticles and WS2 nanotubes? Given that the total volume of data in the world is expected to be reached to 123 zettabytes by the end of this year, how can we benefit from H2 intercalation techniques and WS2 if synthesis methods in order to have a more sustainable and alternative data storage? Or it is even possible to store data in WS2 nanotubes at all? I ask this because I read in a recent Nature briefing that some researchers have tried to store data in DNA double helix. However, they faced some challenges due to the cost of PCR techniques as well as distribution in data when they tried to export it from double helix of DNA. P.S. The current volume of data in the world just exceeds the number of stars in the observable universe. Thank you for the great presentation. The conclusions are way too exacting and full of opportunities.
Thanks for the question. Yeah, in fact, I have to admit that I'm not a specialist in data science and in big data and in AI, so I'm sorry, I cannot fully answer that question, but maybe my question, what I can answer, because there was some comparison with DNA as using as memory one. So here I should admit that these structures may be too simple, because we have these inorganic molecules that are just 3 atoms in periodic structure. So I'm afraid that we don't have much too much possibilities of different type of information storage in so simple structure, unless again we do some kind of functionalization. So if we are able to implant different atoms to gallium or maybe other atoms, then these structures become they're still periodic, but they are more complex. So again, I'm not in this field of data storage, so maybe my answers are not so professional in that way. But still, we are not considering them for this type of research. We are more considering them for use as batteries, and if they are they have electrical conductivity, they have sensory properties, then they can be, of course, involved in a lot of electronic structures, like also in memory devices. But I'm afraid at this moment, not for this application of direct data storage. So this is as far as I can understand this issue. Yeah.
Thank you. Are there any questions? If not, Alex, thank you again for this nice talk.
Thank you very much.
As a memory of seminar, we'd like to give you a gift.
Thank you very much. Thank you for your attention.